Hello everyone, this is Siddiqur Rahman and welcome to the fifth and last lecture of the third week. So let's start. By the end of this lecture, you guys will able to know how to simplify of a Boolean expression using Boolean algebra technique or laws of Boolean algebra. So let's start with the outline. From this lecture, you guys will know various types of simplification. First one is simplify expressing using Boolean algebra technique. Second one is design a logic circuit. Third one is design a logic circuit using logic gates. Fourth one is simplification sum of product, which is in short SOP problems using K-map. And last one is simplification of product of sum problems using K-map. So let's start with the example of simplify expressing using Boolean algebra technique. So let's start. The first example states that using Boolean algebra techniques simplify the following expression. And as you see, the expression says I repeat again, the expression says A and B, or A and inside of the parenthesis B or C, after the parenthesis first parenthesis, or B and inside the second parenthesis B or C. So here is the solution for you guys, and the solution is a tabulated form for your understanding. For your clear understanding, I would like to provide the solution in tabulated form. The first row is represent the first step of the given problem, and if you see, then you notice that the parentheses are vanished in this line, and the right column says which law are used to solve this line. So as we know, the law of distribution or distributive law, and what we get, A and B, or A B, or A and C, or B and B, or B and C. Well, the second step would be on the fourth term. We would like to apply the idempotent law, which is B and B is equivalent to only B. And the third step is also idempotent law, which is first and second term. As you see, A and B, or A and B, which equivalents to or which equals to A and B. And fourth step is, here are three steps are including in fourth step. One is factoring distributive law. After that, we would like to do a annulment law, and the last one is identity law. And finally, we get the simplified version of the given Boolean expression is B or A and C. And another thing you have to notice, at the last line of the table, at this point, the above expression, which meant B or A and C, is simplified as much as possible. So the most simplified expression of the provided expression is B or A and C. So in this way, you can simplify the given Boolean expression. So let's move into the next example. And here is another example for your understanding how to simplify the given Boolean expression using Boolean algebra technique. And the expression, or you can say the given expression, is A or B inside of the first parenthesis. After that, inside of the second parenthesis, you get A or C. And first, the first step would be distribute the first line, or you can say we can use the distributive law, and after applying distributive law we can get A and A, or A and C, or A B, or B and C. After that, the second step would be idempotent AND law. Third step would be distributive law again. Fourth step would be identity OR law. Fifth step would be distributive law. Sixth step would be identity OR law, and seventh step would be identity AND law. And finally we get our final simplified expression of the given Boolean expression, which is A, or inside of the parenthesis B and C. And this is the most simplified expression of the provided Boolean expression. So let's move into the next slide. And this slide represents the similar kind of problem, but not exactly the same one. And here the problem is, or the given expression is A or B, or sorry, I repeat again, A and B, or B or C, and inside of the first parenthesis B or C. And first step would be to solve this expression, or you can say the simplify this expression. We need to apply distributive law, which is A and B, or B and B and C, and last term or last parameter would be B and C and C. After that we need to apply identity law. After that we again in the third step we need to apply identity law, and last step would be factoring distributive law, which is B and inside of the first parenthesis A or C. And this is the simplified expression of the provided Boolean expression. So let's move into the next example, and first read the question. Design a logic circuit having three inputs such as A, B and C. Will have its output high only a majority of the inputs are high. So first and second step would be, for this problem, set up the truth table and write the AND term for each case where the output is 1. Well, we already know this truth table, or we already know this kind of truth table in the previous week, so we don't have any problem regarding this issue, I guess. So if you since the inputs the number of inputs are 3, that's why we can write 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. And if you look back at the question, you can find A, B, C have its output high only when a majority of the inputs are high. So if we look at the truth table closely, then we can find majority inputs are high means 1. In the fourth line of the truth table, you can get 0 1 1 in that which means in this line there the two inputs are 1. That's why we can get in output 1. Similarly 6th, 7th and 8th one also. And if we look at the 7th line of the truth table, then we get 1 1 0, and for this reason the Boolean expression would be A, B and C bar. C bar and a question may arise in your mind, why C bar? Because if you look at the input section, then you can find as the value of C is 0, but we don't need to use 0. That's why we are using a bar of that alphabet. So that's why we can write A, B and C bar. So let's move into the next slide. And here is the continuation of the previous example. Third and fourth step would be write a SOP. SOP stands for sum of product. Form the output and simplify the output expression. We already find out the first line of this expression, which is a bar b c, or a b bar c, or a b c bar, or a b c, and the fine, and if we simplify this expression, then we get at finally, or you can say in finally, bc or ac or ab. And then finally we need to implement the circuit as we get in the previous slide as the simplified version of the Boolean expression, which is the output should be AB or AC or BC. And you can see that in here we need 3 AND gate, because A and B, A and C, and B and C. So that's why we need 3 AND gate, and all AND operator are connected with a OR operator. So we need one OR gate. I hope this will not create any problem for your understanding. So that's all for this problem. So let's move into the next example. And this type of example is so easy because the question states that draw a logic circuit for A or B inside of the parenthesis, after that and C. So we already see from the question that we need 2 gates. One is OR gate and another one is AND gate. And you see A or B. So our OR gate should be 2 inputs, which is one is A and another one is B, and which output is connected with one which output is connected as a input of our required AND gate. So A plus B should be the one input of the AND gate, and other input should be C. So easy, right? So this is another problem like the others. I don't tell about much. So let's move into the next problem. And this type of problem is very important for your understanding. So let's start. Using K-map, determine the final expression for the following SOP problem. As we know in this lecture, SOP stands for sum of product, and the problem states J inside of the parenthesis A, B, C, which represents the number of inputs for this problem, and the right side represents the summation sign. If the problem don't declare whether it is SOP or whether it is POS, then you can understand from the question. If the question consists of a summation sign, then you can assume that this is the problem of SOP. And if the question consists of a pi sign, then you can assume that or think that that is the problem of POS. So let's start with the solution. First step, we need to set up the truth table for this problem. So what we'll get, since the input number is 3, that's why we generate in this way: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Well, and you can see the question again. If you see the question again, then you can find there are 4 numbers: 1 3 6 7. Only in that case we get the output is high. That's why in this truth table we are marked in red marks for which line should be high. One is 1, another one is 3, another one is 6, and another one is 7. And if you see the output section, then only in these numbers you can get the 1. and rest of the numbers are output 0. So let's move into the next slide. Well, using k map, the question for us, the second step should be for this problem, set up the corresponding k map. And we already know that there are 3 inputs for this problem, so that's why we need, since the input number is 3, so we need 2 to the power 3, which is equals to 8 shells. And if you see in this k map, 1 2 3 4 5 6 7 8, I hope you understand how 8 cells are generated. And we only write only 4 cells, which is 1 3 6 and 7. And there are 2 groups in this k map. One is 1 and 3, and another one is 7 and 6. So I hope there is no confusion about this matter. So let's move. Third step would be making first group, since we get 2 groups in the previous slide, so we need the Boolean expression from the grouping. So third step should be making first group and get the product term. Get the product term means, since this problem is a sum of product, that's why we need the product term. And the first group should be 1 and in between 1 and 3, and the 1 represents 0 0 1 and 3 represents 0 1 1. And if you see in between 2 numbers, there will be just one changed, which is the input B. B is the binary number of B is changed. First it has 0, and then when it goes to 3, then it will be 1. So there is changed, so we don't count this for our product term. We just consider which is unchanged, which is A and which is C. And for A we get 0, and for C we get just 1. That's why we write C, and for A we write A bar, because we do not want 0. That's why we need A bar. So we can write from the first group marked red 1, mark on k map, that's why we mention in here. So we get product term A bar C. So let's move into the next slide. And the fourth term will be making second group. As we already know that we get 2 groups from the k map. First one is clear, and we already get the product term. And here is the second group, which is 7 and 6. 7 represents 1 1 1 and 6 represents 1 1 0. And if you noticed from this table, then you get a clear idea. The input C are changed when it goes to 7 to 6. So from when the value of C is in 7 is 1, and the value of C when it goes to 6 is equals to 0. So we cannot count them. We just count them the unchanged value, which is A and B, and there is no 0 value. So that's why we are writing as simple as like that, A and B. So from the group 2, or from group 2 marked green on the k map, we get product term A and B. And the final step of this problem, just adding the found product terms, and we found first product term, which is A bar C. Adding means, or sum of product term should be adding. So that's why the plus sign represents after that A and B. I hope you are understanding this problem. Just practice 2 to 3 times. I hope there is no problem to solve or to simplify this type of problem. So let's start with the next problem. and this problem is the reverse of the previous problem, as we already mentioned in the previous problem. And the problem states that using K map determine the final expression for the following POS problem. POS stands for product of sum, and in this problem we see there are the number of inputs are 3, and in the right side pi is placed before the first parenthesis. So if a problem consists of pi like this, then we can assume that the problem is a POS problem. Okay, so there is no confusion about this. So let's start with the solution. First step, set up the truth table. We already do this. Sorry, I repeat again, we already do this in previous problem, so we don't have any problem. But for the POS problem, we just place 0 at the output section on only these numbers, which is 0, 3, 6, 7. And you if you close look on the table, then you found that the indicated number is different color, and which is also output 0. So one is 0, which is 0, 0, 0, output 0. 3, another one is 3, 0, 1, 1, which is also 0. 6, 1, 1, 0, which is also 0, and the last number is 7, which is 1, 1, 1, which is also 0. If you differentiate the SOP problem and POS problem, then you find in SOP problem we replace 1 in the outputs, and in POS problem we replace 0 in the output for our simplification. So let's move into the next slide. Second step would be the set up the corresponding K-map, and in here you see we get 4 numbers, 0, 3, 6 and 7, and we get 3 groups. One is only 0, another one is 3 and 6, and another one is, sorry, I repeat again, 3 and 7, and another one is only 6. Well, let's move into the next slide. And third step should be or would be making first group and get the sum term. We already know this is the POS problem, which is product of sum, so that's why we need the sum term. Well, and if we see, the first group should be number 6, or you can start with the 0, there is no problem, but in here we start with the 6, so 6 is equals to 1, 1, 0. Well, we get A, B for 1 and 1, and for C we get 0, since the value of C is 0, that's why we place instead of C, C bar. But for POS problem we need to complement this, which is A bar, B bar and only C, and we get the sum term from the above, which is A bar, A bar, B bar, A bar or B bar or C. So let's move into the next slide. Now we need to making second group and get the sum term. We already seen the second group would be consisted of 3 and 7. 3 is equals to 0, 1, 1, and 7 is equals to 1, 1, 1. And you see the A input is changed 0 and 1 when it goes to 3 to 7, but in B and C there is no change. That's why we have written here unchanged 1 and 1. We get B and C, but we do not take in this way. We need to complement of this input, so that's why we write B bar and C bar, and the sum term would be B bar or C bar. Let's move into the next slide. And in here we have another group which is third group, and only it consists 0, which is 0 0 0, and we can write a bar, b bar and c bar just like other groups, and we need to taking complement, which is a b c, and we can write a b, a or b or c. And last step would be multiplying the found sum terms, found sum terms, which is already mentioned in the question. POS stands for product of sum, which is we get three groups, we get three sum terms from three groups. So we can write inside of the first parenthesis a bar or b bar or c, second inside of the second parenthesis b bar or c bar, and the inside of the third parenthesis a, b or c. I hope you understand the two different kinds of problem. One is solve problem and another one is POS problem. I hope there is no problem to understand. So let's move into the next slide. And in the next week, and the first lecture would be combinational logic circuit. And thank you so much for your attention. That's all for this lecture and as well as week. I hope you will understand the whole lecture of this week. That's all from my side. I see you guys in the next week and next lecture. Thank you.